Some of the really important things, I think, for freedom people to look at is the reality of the situation we live in. You know, you'll hear politicians talk and say, you know, vote for my party, vote for that party, I'll do this for you, I'll do that for you. And I was just having a conversation where I was talking to someone and we said, well, we know politicians lie. So the stuff that they tell us we know isn't true. So what really is true? All right, this country and people of other countries suffered a horrible terrorist attack on September 11th, 2001. But some of us don't really feel confident that they've really identified the right terrorists. In other words, somebody committed a nasty act where a lot of people got killed, and who did it. So, you know, a proper investigation of a crime scene would involve roping off the area and, you know, doing a real forensic analysis of everything. But on the days following September 11th, they carted off all the evidence, and they were very careful about it. They put it in trucks, and they had GPSs on the trucks, and they monitored the truck drivers because they didn't actually want a single bit of that evidence to be really looked at. And I heard a story once that one of the truck drivers stopped and took a break and had lunch at a diner or something, and they swooped down on him and fired him and got rid of him and all that because he didn't take the stuff right to the dump. He must have been doing something with it. So why did they want to make sure the evidence was destroyed? A lot of people have questioned the government's commission report on that tried to analyze what happened, and they essentially, in my mind, what they've done is essentially tried to set the myth in stone of what happened. So what it's taken is a bunch of independent folks to analyze what happened, and so there have been people all over the country, and one of them is with us today, who analyzed the dust, because when they hauled off everything else, Rudy Giuliani told them to hose down the streets and wash away all the dust too and just run it down the storm drains. But they couldn't possibly get all of it. I mean, if the number of particles of dust would be in the quintillions of pieces, and it blew everywhere. It's in New Jersey, it's in Brooklyn, it's in downtown, it's in uptown. Today we have with us Mark Basile. He's analyzed some of that dust, and he's going to tell you what he found in it. I'll just leave the rest to Mark.
Thanks, Jeff.
Take it away.
It's great to be here. Yeah, my name is Mark Basile. I'm a chemical engineer by education, is my education, but if you would, next slide. And I've analyzed some World Trade Center dust, and I'm really going to tell you about what I found, why I did it, and you'll see. There's a little bit of, my history, what I've done. I got a BS in chemical engineering from WPI, that's Worcester Polytechnic Institute, back in 1986. Even before I got my degree, I was actually working in industry already. So I've actually got about 30 years in materials analysis, materials studies. That's basically what I've done in a lot of my work, is try and understand contaminants, what's in materials, what should be there, what shouldn't be there, what their properties are. I've basically spent my life analyzing materials. The last 12 years I've actually worked for a major instrument manufacturer, and I basically design chemical detection systems and do proof of principle experiments to make sure that they do what we want them to do before we turn them into a product. So that's basically me. Why did I even think about analyzing World Trade Center dust? Pretty much I had some questions from the beginning about the whole thing. I've had questions about the government for a long time. I kind of characterize myself as somebody that lives outside of the box, if you will. But I didn't really know anything. I just had questions. But I pretty much just started to try and follow the little bits of real scientific work that some people were doing, and just try and keep abreast of it. And I pretty much just kept informed. And there were some reports that came out. There was a company by the name of R.J. Lee, and they basically did an environmental study. They had done these long before the World Trade Center disaster happened. They had a huge database of particulate matter from the city of New York City. They had, understood understood environmental implications in the city. Well, after the catastrophe, a number of people, Deutsche Bank being one of them, hired them to come in and evaluate their building that was partially damaged, not completely destroyed, but partially damaged. And they basically wanted to know what's in the building, can we send people in there, what do we have to do to recover this building? So they hired R.J. Lee. R.J. Lee went in and they basically, collected samples of dust all through the building, and they started to find some things in there that they had never seen in dust in New York City before. And that was basically, well, they're one of them, but USGS did, that's U.S. Geological Survey, they did some particle surveys. They collected dust and they went in there and they looked at it and analyzed it, and they found these iron microspheres. And basically what that told them was that there were these very, very high heat conditions that produced molten steel, molten metal. They found actually even a molybdenum microsphere. They found most of them were iron-based. So the steel had to be heated up to the point, or iron-based materials had to be heated to the point where, they were molten. And the thing is, jet fires, hydrocarbon fires, don't normally produce conditions where they can actually melt steel. We've all looked and experienced things like wood stoves. They don't melt, do they? You can get that fire raring and roaring in there, but it doesn't melt. It may get warped, it may do some funky things over time, but they don't generally melt. So these fires really weren't expected to produce iron microspheres, but they're especially not expected to produce molybdenum microspheres. Molybdenum doesn't melt up until well above 2,000 centigrade. It's a refractory material. It's used in very high heat applications. You could do it through an electrical discharge, but anyway, there were certain things that a lot of different people who did various real scientific work saw in the dust that made me say, some things aren't quite right here. The EPA even, one of the big things that they saw were these environmental outbursts. They basically did a lot of gas sampling, of what was coming off of the debris fields. And if you go in and you look at the time traces of what they saw coming out of the debris fields, there were certain spike events that occurred over a period of a couple of months that produced some materials that had never been seen in environmental sampling before. And some of those materials are associated with thermite and nanothermite. So there were just a lot of questions that actually started to come up if you really went and took the time to follow the bits of scientific information that were gathered early on that should have raised some eyebrows. They raised my eyebrows and gave me some questions. So that's really why I started to seriously, look into this. All right, some of the things, if you look through the R.J. Lee report, that are significant statements that they make are, one is that there's, in this, well, I've got a pointer, I forgot, right in here, there's what's called a World Trade Center dust signature. This stuff is very different than normal dust. It's got a huge amount of asbestos, it's got a huge amount of gypsum dust, it's got the iron microspheres all through it, it's got red-gray chips that we're going to talk about. It's a very distinctive signature to it. It's not like normal dust that you would counter anywhere else, and that's one of the things that R.J. Lee says is they've made a living studying dust, believe it or not, as part of what they do, what's contaminating areas, and they'd never seen anything quite like this before in all their experience. They saw, one of the things that they saw in here was this heat-affected materials. There was asbestos that was melted, there were glass fibers that were melted, there was molten steel, these iron microspheres, and I'll actually show you some pictures of those. But there were a large number of materials that were highly heat-affected, which, okay, you say, yeah, I mean, we all saw the explosions and there was a lot of heat there. I won't take that away. There was a lot of heat. But a number of the materials that got affected in the way that they were affected showed temperatures that were well above what should have occurred inside that building. And we'll talk a little bit about that. So R.J. Lee attributed it to, the building fires and all the cataclysm that we all, have seen over and over again on TV. But I don't buy it. I don't buy it. And in fact, actually, I'm not the only one that doesn't buy it. If you go and you read NIST's actual reports and their estimates of what the temperatures were, along with a lot of other groups of scientists who've made their best estimates based on their experience with things that have happened in the world before, they all say that the temperatures inside the building shouldn't have melted the steel.
Sorry, can you remind me what NIST is?
Sorry, it's the National Institutes of Standards and Technology. It's a government lab, in essence. They're a big organization. They have a number of different facilities, but they basically are some of our top scientists, and they pretty much try to set the standards for either measuring things or analyzing materials, or they're basically just a government standards organization that brings a lot of expertise to understanding various problems, like atomic clocks, or you name it. It's they get involved if it's a serious problem. People need to work on it. So, all right. Another study that pointed out a lot of problems here too was the FEMA. That's the Federal Emergency Management Association, or agency, I forget exactly, but Federal Emergency Management. They did a study. They were charted basically with trying to explain why the buildings fell down. Because in all the experience of the world, no other structural steel frame buildings have ever fallen from fire. And if you go and Google, you can see some real torches. Like in Madrid, there was it wasn't 110 stories, the World Trade Centers were the world's tallest buildings, at least at one time. But it was like a 47-story steel structural building. This thing burned like a torch for 24 hours, and it didn't fall down. Unlike the World Trade Centers, which, they didn't have a plane fly into them, but the temperatures in the Madrid fire were really crazy. But anyway, FEMA was charted with explaining why the buildings fell down, and one of the things that happened was, even though a lot of the material was carted away and destroyed and smelted away over in China, a few beams did come out of the debris pile that were not quite right. And there was a group of scientists that worked at WPI, just happens by coincidence to be where I went to school, but they have a really good fire safety engineering program there, and they also have some really good top-notch material scientists. So basically these beams that came out of the World Trade Center debris pile wound up at WPI with a few professors there to analyze. They worked on them, and they basically put together a report. And what am I saying here? Okay, so this is basically just explaining about, the beams, where they think they came from, that they came from 1 and 2, possibly, and they think one of them, I think it says definitely, probably came from World Trade Center 7, which is the third building that fell that day, which didn't get hit by planes. So they basically got these samples, and I'll show you some pictures from their report, if you would, the next one. But first, one of the things that they say in there is that the steel that was used in the building, is the alloy, is what's called A36 structural steel, and we'll get into that a little bit later. But basically, one of the things that they talk about, and this is a real critical paragraph here, is they talk about evidence of attack on the steel, including oxidation and sulfidation, and we'll get into sulfidation particularly, although oxidation is important too, with subsequent intergranular melting. Okay, so here we have melting of steel beams, was readily visible in the near surface, what does it say, microstructure. The sulfur-rich liquid penetrated preferentially down grain boundaries. I won't read the whole thing to you, but okay, they talk about a eutectic, and this is kind of important here, is they talk that the temperature of the steel approached 1,000 degrees centigrade. Steel normally melts up around 1,500 degrees centigrade. But there's some wonderful tricks that science has taught us, and we'll talk about those a little bit later. And you can miraculously melt steel at lower temperatures if you do just the right things. But we'll talk about that. But basically what they talked about is that the A36 steel was attacked by something that had the ability to melt it at lower temperatures than steel normally melts at. This is an example of one of the beams that they pulled out. You can see this material up along the edge. This is all molten material. These holes and these areas where it's been eaten away, that should be a solid steel beam. There shouldn't be any holes in these steel beams except for where they put the bolts through. And these aren't bolt holes.
Is that an I-beam?
Yeah, it's hard to see. Well, there were a couple of different ones. There were I-beams. There were also some L-beams, flange-type assemblies. And but you'll see some other pictures as we go through here. If you would, the next one. But that one shows melting along the edge, holes that are eaten straight through the steel beam. This is basically where they've taken, this is this L-type structure. that I'm talking about. This one right down here, what they've basically done here is they've cut a small piece away and they've mounted it into a piece of plastic, like an epoxy. If you take a two-part epoxy, a typical way to mount these specimens is you take your specimen, and this little curly object here is actually just a little like clip that holds the specimen in place. You pour the epoxy into a encapsulate it, and then you start polishing and etching to reveal the microstructure inside. And the epoxy is just there for what's called edge retention, because whenever you sand something, you'll tend to round the edges over, but by encapsulating it, you keep those edges preserved. That's all that thing is doing, is it's really just holding a piece of steel that could then be lapped and etched to reveal the microstructure inside the steel. Those are just the techniques that are used. But basically what they're pointing out here is, if you look at this, right in here, see how it gets really thin? Again, it should be a uniform thickness. Something's eaten this material away in there. If you would, go to the next slide.
I'm sorry to interrupt.
Yep, no, ask questions as we go.
Is this stuff part of WPI's research, or is this...
This is all up until, as soon as I start talking about stuff that I've actually done, I'll let you know, and and so on. But yeah, this is all just other people's work that got me started. These are the things that made me question, what was really going on. So this is really just some of their detailed work where they're showing you this material that was melting into the steel and so on, and they go in and they do some compositional analysis, and basically what they found is that it was basically an iron-sulfur-oxygen mixture. But the thing that's wonderful about that, in its own way, if that's what you're trying to do, because there are people who make materials that do exactly this, and they tailor them specifically because of these capabilities. What's happening is it's, well, I'll give you an example. Lead and tin. Okay, we all know solder, that's a mixture of lead and tin. If I have lead and tin at 100% composition, they have certain melting points, but when I begin to mix them together or melt them together, there's a certain mixture that has the very lowest melting point. The mixture's melting point is lower than each element by itself, and that particular composition that has the very lowest melting point is what's called a eutectic. And it's really just a single-phase system that has the ability to melt and be liquid and be of a certain composition, turn solid at a very specific melting point. It's not a range, it's a very specific point. And it has the same composition as a solid and a liquid, and that's a eutectic. Well, iron has the ability to form eutectics with oxygen and sulfur. And when it does, the melting points of those eutectics are 900 to all the way up to 1500 degrees, all depending on the composition. But the thing that iron, along with sulfur particularly, but also oxygen, is if you do it just right, you can lower the melting point, and you can cut through a steel beam at much lower temperatures than steel would normally melt. And people do specifically formulate together materials to do exactly that, and we'll talk about it a little bit later. So one of the things that they talked about in their report here is how they saw this severe corrosion, erosion on beams and so on. And right in here they say it's also, it is possible that this is the result of long-term heating in the ground following the collapse. We all know how hot the debris piles were, or at least that's what we've been told, and I think they were actually really hot. But we could all debate about why that was. So they say these beams could have been attacked afterwards, but they also say it could have happened before. And what they weren't necessarily thinking that there was malfeasance involved. And I've even spoken with some of them. Okay? But what they were concerned is, again, they're a fire safety and a material scientist group. If there's something in buildings and having fires in them that can cause them to collapse like this, we all need to know about it, and we need to do things accordingly to make sure that this never ever happens again. So what they're pointing out here is that this could have happened before the collapse or afterwards. They're not really sure. They're just putting it out there and saying, now personally, based on everything that I found, I think it happened beforehand, but we'll get into that. But even they, a group of totally independent scientists with no agenda, just simply trying to make the world a safer place for all of us, said this could have happened before or it could have happened after. So my assertion here is if the fires didn't melt the steel, because they're really not capable of doing it under the conditions that existed in the World Trade Center. Okay, I don't know how many of you follow various things, but you'll hear claims that hydrocarbon fires can't melt steel. They simply can't achieve those temperatures. That's actually not true. If you have the right conditions, and and I won't get into a lot of science, but I'll simply leave it. If you go do your homework, you can find resources that will tell you conclusively that jet fuel can get temperatures that will melt steel. But you have to have very, very strictly controlled conditions to do that. And I don't think those conditions existed in the building, okay, to be perfectly honest with all of you. So when you hear that, it's not strictly true. It's generally true, but it's not strictly true. But I don't think that the fires that we all saw are what, or at least the vast majority of what we saw, although I'm going to show you some pictures of some fires that I think might have been involved in melting the steel. But all right, so, and I say there were several incidents, and that's what we'll get to next. So I don't know how well you can see this, and I don't know if any of you have seen it before, but basically what it is it's a view of the World Trade Center. I think it's World Trade Center 2, but basically right around the vicinity of the 80th floor, and I'm sure you can go online and Google this. Basically what's happening here is there's a yellow stream of fluid coming out of the building here, and there may be one just above it, I'm not sure. There was this yellow glowing material seen flowing out of several locations out of this building. There aren't a lot of glowing yellow things other than like the stuff that's in glow sticks, other than hot metal, if you know what I'm saying. So this was probably a molten metal of some sort. A lot of people have said, well, it was probably just aluminum from the airplanes, because aluminum melts at a relatively low temperature. It's like 600 centigrade. Oh, this is simply just another view, and you really can't see it. It's even fainter. But there were some other views taken by other photographers of the same type of effect coming out of slightly different locations, but in that vicinity. All right, what this picture is, and again, you can't see it very clearly because the light situation, but basically it's a picture of molten aluminum over here being poured at a foundry. It doesn't glow yellow. Molten aluminum doesn't glow yellow. This is a cupola. It's a furnace cupola pouring molten iron. It does glow yellow. There are specific reasons why aluminum doesn't glow, and it basically just comes down to it's a radiation energy balance. Okay, all materials basically when they interact with radiation can absorb it, they can transmit it, they can reflect it, and they can emit it. And when you sum those functions around a material, they basically come to 100% or unity. Okay? Aluminum is very, very reflective. Like 90% of the light or 80% of the light that hits it is reflected. If it's reflecting 80% of the light, it can't be emitting more than 20%. Okay? And so basically what it comes down to is aluminum does not emit radiation very well. And so when you heat it up, it doesn't tend to glow very well. Whereas iron is not a very good reflector, especially at these temperatures, and it has a very high emissivity. And so when it gets really hot, it glows very brightly. So the material that was flowing out of that building was not molten aluminum. Unless it was literally probably above its vaporization temperature, then maybe it would be hot enough to glow like that. But it just doesn't glow like that, so it wasn't aluminum. All right, the next thing I'm going to talk about here is just basic thermite. If you know anything about the World Trade Center and you've been following it, you've probably heard the term thermite. All thermite is traditional thermite is aluminum, powder generally, and iron oxide. That's traditional thermite. It doesn't have to be just those two. You can do the same thing with aluminum and copper oxide. You can do the same thing with aluminum and molybdenum oxide. You can do the same thing with aluminum and a lot of other metallic oxides or oxides in general. But traditional thermite is iron and aluminum because it just works real well. And it produces molten iron. And traditionally it was used for things like welding railroad tracks. when they would have two rails, they'd set up a crucible above that, and they'd put in thermite above it, they'd ignite it, and then they'd open a door below, and there'd be a little mold frame, and it would actually just let molten iron down in, weld the two tracks together, and then they'd grind it to final form. That was one of its earliest applications. One of its more traditional uses today is by the military. When they want to decommission a piece of artillery or any type of equipment, they take what's called a thermite grenade, and they'll send it down the barrel, in this case generally. It does not explode. It simply burns, produces a huge amount of heat, and produces molten iron, which melts again at 1538 centigrade, but it's also so hot that the aluminum oxide that gets formed as one of the other products, and we'll get into that a little bit, is also molten. And aluminum oxide doesn't melt until over 2000 degrees centigrade. So it's incredibly energetic stuff. So when they drop it down there, what it does is it doesn't explode, but it just ignites, and it produces a blob of molten steel or iron that will actually melt through the steel barrel and basically decommission that tank. You can't fire it, at least not very well if it's got a big hole out the side of it. So the real key here to what makes thermite happen is we've got aluminum, and then we've got iron oxide. Again, you probably can't read this real well, but basically what happens is the aluminum loves the oxygen. It's a much stronger, I'll say, grabber of electrons, if you will, or giver up of electrons. It gives them up. But it basically steals the oxygen from the iron oxide. It takes it. It just literally goes in there. It's the bully on the block of the group. And he goes in there and he says, I want it, it's mine, and he takes it. And so the iron gets left alone, but along with that, there's a huge amount of energy release. You could think of it as a horrible fight, right? It's just this huge amount of energy that gets released, and everybody gets liquefied because of that. There's a little trick that you can play with thermite, and people have done it. And then instead of being called thermite, they call it thermate. And all they do is they add a little bit of sulfur. You still let the aluminum grab the oxygen from the iron, and he produces a huge amount of heat. But because you've got sulfur there now, it alloys in with the whole mixture, and it basically forms that iron-sulfur eutectic that I spoke about earlier, that has the ability to melt through the steel at much lower temperatures. And you can go do patent searches and put in thermite, thermate, building demolitions. There are patents. People make a living making various charges that have the ability to cut through steel beams. They do, yeah.
Oh, I'm sorry, but you probably saw the YouTube video. Was it about the iron worker during the demolition, and they were interviewing him and asking about it? And I mean, I'm a welder, so like the beams were cut at a 45, and you see the molten slag coming off of it. And he asked the demolition worker, would an iron worker actually do this? He said, no, that either they're a hack or nothing would produce that amount of slag off the steel beam. But so that, I don't know if you saw that video.
I've seen some, yeah.
Least efficient way to cut the beam.
Yeah, it's right at a 45 is what slips and comes down. But they're saying he's basically saying and being a welder, obviously you don't have your oxyacetylene torch set properly if you're getting that much on a slag. But would the thermite, would that produce the molten
there'd be a slag. There'd be a slag. But, it all depends. Again, I can only speculate about whatever, but some of the devices that I've seen, what they actually do for doing exactly what I'm talking about is they take the thermite, and you know how I said it doesn't explode? There's really no gas, per se, produced, although there is, and if you look at some of the World Trade Center films, a lot of, like in those, when those molten metal events were occurring, there was a whitish smoke that came out of the building at the same time. And the aluminum oxide that I referred to, when it gets hot enough, some of it will vaporize and come off as like a whitish smoke. It's a very clean white smoke, whereas a lot of the smoke that was coming out of the building at that point had gone black because it was oxygen deprived. And But what they do in these devices, they load them with the thermite or the thermate, but then they actually add a material that does produce gas when it gets hot. And what they do is they shape the charge so that it has a nozzle, so that what actually, and they make it basically almost like out of ceramics, high temperature refractories, almost like a rocket engine, so that as the thermite burns and then the gas begins to get produced, it produces a thrust of sending this liquid iron out this constricted nozzle to give it a momentum and a impact when it comes into the beam. So there are patented devices out there that use the, thermite or thermate in a controlled manner to slice right through beams, and there's a lot of different types, but that's just an example. To get to my analytical work. So this is all the stuff that, makes me question, could it be done? What's going on here? Does it all make sense? Well, in December of 2007, there was a 9/11 conference in Boston, and Stephen Jones, who's one of the earliest researchers who started looking into the World Trade Center desk, was coming to talk about his work with the iron microspheres and what he thought about them. So I said, well, geez, I live 30 miles away. I'm going to go down and, listen to him. So he gave his talk, but during it he says, I've discovered this new material in the dust, more than just microspheres. I found these red-gray chips, and they seem to be thermitic. So I listened to his talk. I asked him a couple of questions. They had an open mic, and then afterwards I basically just approached him and I said, I'm a scientist, engineer. I can do a lot of what you've done. He showed the techniques he had used for analyze them and so on. He said, I have this capability. Can you put me in touch with somebody, and I'll get a sample of the dust for myself and see what I see. And so he did. And basically about 2 weeks later, he gave me the name of a woman from New York City, Jeanette McKinley. She's one of the 4 people that supplied him of the 5 samples that are in his peer-reviewed paper. And I have a copy if anybody wants to see it here. But she was one of the people who supplied him a sample. So it was really a real confirmatory for, what he was preparing to ultimately publish. So she sent me a few tablespoons, and I started my work. So this is an aerial view. Again, you can't see it real well, I'm sure, but this is basically the World Trade Center complex, and most of it's demolished at this point. Her apartment was basically directly across the street at 110 Liberty Street from the World Trade Center. Sorry. When I think about her. But anyway, she was home when it happened, and she basically had to run out the back of the building. Luckily, she survived and stuff. But she's an artist, and when she came back, she collected a bunch of it to potentially use in her future artworks. And so anyway, I wound up with some of it. So how do you get the things that we're interested in out of the World Trade Center dust? It's actually incredibly simple. Anybody here can do it. Okay? If you can get yourself a sample of World Trade Center dust, all you need is a baggie and a magnet, and you're in business. Okay? That's it. These microspheres are magnetic. A lot of these heat-affected silica or mineral wool, asbestos, a number of those that were heat-affected and turned into spherical particles, or even some of them are teardrop shaped, a lot of those actually have iron microspheres inside of them. I'd love to know how that happened. But anyway, so they're actually, when I started getting glass particles attracted to my magnet, I said, what's up with this? Because glass isn't normally magnetic. But when you look inside, you can see iron microspheres captured inside there. But the other thing that was attracted to Stephen Jones's magnet, and ultimately to mine and anybody else who wants to go do this, are these red-gray chips that we're going to really specifically talk about now. But that's really, the way I like to do it is I take a small sample of the World Trade Center dust, I put it into a Petri dish, and I put it under a stereo zoom microscope. And then I take my magnet and I put it underneath the dish. And so what I can do there is I actually can see, well, when I get an iron microsphere attracted, I can bring that over to one side of the dish, and when I pull the magnet away, it stays there. And then when I get a red-gray chip, I can pull it over to this section of the disc and again pull away and leave it there. So I can pretty much separate even within the dish as I'm doing it. I can begin that segregation process. But that's all that's involved. You can get these materials of interest out with a magnet. That's all you need. And a microscope or a magnifying glass helps to see them, but that's all you need. And you can begin your work. So what I'm showing you here actually, and again I apologize you can't see it, but down here you can probably see a sphere. It's a little ball. That's actually one of these iron microspheres. And there's an elemental composition that's given up here. Basically, the way I analyze these is I put them into an electron microscope, and they get hit with a high energy beam of electrons. And when you hit things with a high energy beam of electrons, they give off X-rays. That's just what they do. And the energy or the wavelength of those X-rays is dependent on the element. So you'll notice, if you could see it well enough, at the top of each one of these little peaks, there's a little symbol. I think that one might say Fe. That's iron. So when I get a peak at a particular wavelength or energy, that tells me it's iron. When I get one, at the appropriate location, it tells me it's aluminum or silicon. So it tells me all the elements that are in, and if you could see it, somewhere on this ball there's a little circle, and that's the zone that I'm actually analyzing on that sphere. Well, anyway, to make a long story short, it's mainly an iron microsphere, but the other thing that's interesting about it is there's no manganese. If there was manganese there, then there's a good possibility that it was melted A36 structural steel. But if there's no manganese, then it was not A36 structural steel. Now, that's not the only steel that was in the building. Like on each floor, they were basically concrete floors, and there were actually galvanized steel pans under that. So not every bit of steel in the building was A36 structural steel, but all I'm getting at is that this microsphere was not A36 structural steel, and the vast majority of them are not A36 structural steel.
In your chart, there's looks like 3 different FEs.
Yeah, well, it gives you different peaks because it comes from different shells within the atom. What it's actually interacting with is these innermost shells. Those are the highest energy electrons, and so when they get hit, those are the ones that produce these X-rays. The outer electrons tend to produce things like light, which is also an electromagnetic radiation, but it's much lower energy. And so those outer electrons give us light, the inner ones give us X-rays and gamma rays and all sorts of good stuff. But all right, so anyway, this is a microsphere. This is just a composition of, you could go to the next one, of A36 structural steel, and you can see here that it's basically about 1% manganese. So if you're looking for A36 structural steel, you want to see that.
Do you think that the steel decking probably, could that have been, what portion would you say is structural steel versus decking?
In the building?
Yeah. I mean, would there be...
I don't know, but there are actually people who've done a heck of a lot of work.
The rescue workers said, they didn't even find, a piece of a telephone was the largest piece of recognizable debris. So, the decking, I don't know.
Yeah, from what I understand, you're exactly right. The whole buildings were basically obliterated. They didn't just fall down and give you a pile of rubble that was 110 stories high. Because each one of those concrete decks, again, I forget, but I'd refer you to a website. It's, not Architects, although there'd be a good one, Architects and Engineers for 9/11 Truth, but there's the Journal of 9/11 Studies, I think is what it's called. And there's a lot of real good scientific work that's been accumulated there. And there are people who've specifically spent a lot of time trying to catalog exactly how much steel, what types, how much concrete.
I didn't mean to sidetrack you.
No. Yeah. But it's a good question. But it is... the thing was obliterated, and from what I see in the dust, but I was only being given samples of dust to begin with, so these are some pictures of actual red-gray chips that came from dust that I've analyzed. It's just 2 different chips. This one, I think I'm showing you the gray side up, and this one is actually the red side up with the gray material behind it. This is actually, it's the only one that I found, although I've heard from some of the other researchers that they've also found some multi-layered red-gray chips. This one actually appears to have an outer ceramic layer, then a red, then a gray, then a red. It actually goes up about 5 or 6 layers. I haven't done any further work, and it's heat affected on the outside too, so it saw some heat somewhere along the way. But I'm saving this one for a particular experiment when I finally do get one last piece of equipment, access to that I really want to to get this one into. But this is a picture here. This is just another red-gray chip, but it's a specific red-gray chip. It's what I call red-gray chip number 13, and as you can guess, it was, fortuitously for me though, it was a lucky 13. It's one of the bigger chips that I found. This chip here, it's all blown up and magnified, but it's actually about 2 millimeters across by about 1.6 millimeters across. It's relatively small, but that's the biggest one I found. This is really just some analytical work that I did on the red layer. This is over here is really just a piece of that red material that I broke off freshly with a razor blade to expose the material that was inside to get a fresh, uncontaminated surface to go in and analyze. And it's basically made of, in large part, there's an organic material of some sort in there, a carbon-based with a lot of oxygen, but the basic real matrix is also composed of silica, which is like in sand, and we'll get into a little bit more detail maybe. But there's also significant quantities of aluminum and iron, which are our key essential ingredients for thermite. So all I'm really saying is the same thing here, that it's an organic matrix, it's silicon rich, but it's also got significant quantities of iron and aluminum. I want to get a DSC, access to a DSC. That's a calorimeter, and it basically measures energy flow. I used to have one in a lab many years ago, but I don't have one now, and I need one. Anybody know anyone with one? But no, okay.
I know
I'm joking.
Somebody that goes to MIT.
It would help. I've contacted some people there. Do you know his name? Well, we can talk about it afterwards. I'm trying to find one that's close to me and convenient. I have access to one down in Jersey potentially, but that's not real convenient for me. But anyway, just because I don't have this one instrument doesn't mean that I can't go off and maybe still learn some of the things that this machine would have helped me to learn in maybe a little bit better way. So what I did is I set up a little instrument where I could basically control heat these chips. And I basically made up a little apparatus with a stainless steel heating strip that I could electrically control and heat, just to the point where these chips would ignite, because we know what their ignition temperature is based on other scientists' work. So I can basically, in a controlled manner, bring these chips up to the ignition temperature, watch them ignite with my microscope and camera, and you're about to see one, and then go in and analyze what's happened after the chemical reaction, and that's what you're going to see here. But basically what happened is that chip ignited, and what you see, and we can go, anybody that actually wants to see it, we can watch it on the laptop over there afterwards, and I'd welcome you to do that. But basically what you're going to see is, on the left-hand side of that chip, you're going to see a sudden bright flash. White-hot flash, and you're going to then see a wavefront move through the inside of the chip because it's so bright inside that it's actually radiating through the material that's still surrounding it. And you basically see a bright flash progressively move through that chip and then extinguish. So it moves from left to right and then extinguishes. And it's like, okay, you know, it's not overly spectacular, but, you know, something happened there. So this is basically that same chip afterwards, and it pretty much it puffed up, and you could see gas escaping from it. And so it's basically become porous on the outside with actually some holes that burst through for the gas to escape out. And that's just the other side of the chip, showing you again how it's, you know, been changed. What you find inside the chip after it burns, and what I'm pointing here, and you can't see them very well, but there's all these iron droplets now that have, you know, from the reaction have basically fallen to the bottom of the chip, and then when they cooled, they've solidified. So they're not perfect spheres. The spheres form, because we call them the microspheres, when a material is liquid and it falls through air, the only real force acting on it primarily is its own surface tension, and so it tries to minimize that surface area, actually, and hence the surface energy, and it goes into a sphere because that's the minimum surface area for a given volume of material, and so you wind up with a sphere. These don't form into perfect spheres. They're trying to, but when they hit something, they flatten out. But you basically wind up with all these metallic iron-based droplets that get formed inside the chip. And the other thing that they don't all form into droplets. The other interesting thing is as these are actually burning down through the chip or melting their way down through, they actually along the walls leave this very thin film of solidified iron. You know, whereas if you take these chips before you ignite them, and I've done it, just like I did where I said I exposed a fresh section, I've cut into these chips dozens, if not hundreds of times, and I've never found an iron microsphere inside. I've never found a film of iron inside. It's not there until the chip reacts. When the chip reacts, it produces molten iron, and you get that iron there. There's no iron, free iron. There's iron oxide before you ignite it. But there's no free iron inside these chips. It's only after it burns and it reacts that the thermite, you know, it's the same in the thermite grenade. If you open up a thermite grenade, you're not going to find any iron inside. It's not there. It's all tied up in the iron oxide. But after it reacts, there's plenty of iron.
And that's molten iron. And
when it's first produced, it's molten. And ultimately, it'll cool down because the universe around us isn't 1,500 degrees, right? It'll cool down and it'll turn solid again.
But that's what melts the steel?
That's what melts.
Yeah. Turning it into the molten iron, then that melts.
It has the capability. I'm not sure exactly what they did. I think they did a few different things. Because
1,500 Celsius and Fahrenheit.
To get the exact conversion, you would multiply it by 1.8 or 9/5, and then you add 32. But just as a general rule, you kind of almost want to just double it. It's a little bit less than that, 20% less than doubling it, roughly. So 1,500 doubled up, would be 3,000. Then you take away 20%, and you're down to 2,400. Fahrenheit. So it's basically, 1.8 times the Fahrenheit. And then, when it's big numbers, the 32 becomes kind of insignificant, if you know what I'm saying. Is it 2,400 or 2,432 Fahrenheit? It's hot,
Comes at 2735.
Oh, 27? Yeah. So, but it's, multiply it by 1.8 and add 32. This was really just to zoom in on another iron particle. Again, you can't see it real well, but right there is a specific iron droplet, and then right next to it is some of the shell left from the original matrix. That's the leftover silicate material that's all coated inside with these iron films and so on. And again, I can't stress enough, that iron's not there until it reacts. It's just not there. This is just an analysis of that specific iron droplet, and again, it's iron rich. There's no manganese. But the other thing that's in there, though, is silicon, aluminum, and in some cases we get sulfur also, but it's also alloyed with aluminum and silicon. Silicon also wonderfully has the ability, when it's alloyed in with iron, to again lower that melting point. It gives excellent fluidity. That's why it's actually alloyed in a lot of cases with metals. It makes them very easy to pour when they're molten. So silicon will do the same thing. So I think that may have potentially played a role too. So in the dust we have iron-based microspheres, indicating that there were temperatures there that melted iron-based material. Something did that day, and it melted a hell of a lot of it, to use the technical term. Because this, when you look at dust, there's a lot of these microspheres in there. They're not just, a minor insignificant component. R.J. Lee saw enough of them that they even commented on them, like, wow, where the heck did these all come from? I guess the other thing that, the red-gray chips, the red layer is the thermite. I'm still not sure what the gray layer is there for. I could speculate, and other people have speculated, but I'm not really sure why it's there. But it is, and but it's the red layer specifically that's thermitic. that produces the iron droplets and that contains the energy. And if you were to go and read some of the reports of the people that develop these types of materials, they work like at Lawrence Livermore, it's a national laboratory. And one of the things they bragged about in some of their articles, because they're developing stuff for our defense industries, so they want it to be as utilitarian in creating destruction as it can possibly be. And one of the things they brag about in their articles is that based on how much aluminum, how much iron oxide, and what other things they add in there, they can basically control the burn rate. They can wind up with a chip that gets a very slow burn. They can get a chip that has a very fast burn. But also when they add other things in there, they can then get like huge gas. You know, I said thermite doesn't explode, but if you put things in there with it that when they're heated produce a lot of gas, you can produce an explosive mixture using thermite as the drive engine. So they talk about all these capabilities by playing with the composition and tailoring the specific size of the particles and the distributions and the quantities to get something that will just melt through steel to something that creates a huge explosion. So that's where I go to with, I'm not sure exactly what they did with these things, how they used them, in what manner, but what I can tell you is that they are there. They shouldn't be there, at least not in the universe that I live in and the one that we've all come to think is what's supposed to be surrounding us. All I've done for 3 years since I knew that this was here is try to come up with a reasonable explanation. I still can't come up with one. And if somebody can come up with one, I'm all ears. But it shouldn't be here. So I think it raises a lot of profound questions, and we need a new investigation. Why did I find thermite? Well, because I think it was used to take the buildings down, and the real question is who put it there. You can't really see this real well, but basically it's a picture of George sitting in the classroom that morning, and there were a lot of real weird coincidences that day, if you really start to look into it. But I think that a good coincidence, for what little bit of goodness there is in it, I take a lesson from it, and that's why I've put it here. So there's a little sign sitting behind him, and it says, "Reading makes a country great." And I can't agree more. The thing that's put me in the position where I can do what I'm doing here is the fact that I've read and I've learned. So get out there, learn, and do what you can. I don't like him one bit, but I like the sign that's sitting behind him because it's an important message for everybody here. Learn, learn, learn. Don't just take what you see on the stupid boob tube. And there's a reason why they call it the boob tube, right? But get out there and learn on your own. That's why I did what I did here, because, like I said to Stephen Jones, I want to see for myself. I want to see for myself. So, here I am. Yeah.
Thanks, Mark.